Right now, you're sitting on a planet that's part of a galaxy called the Milky Way. It's huge. So huge that light, traveling at 186,000 miles per second, takes 100,000 years to cross it. That's already impossible to really comprehend. But here's what breaks your brain. Our galaxy is nothing. It's a speck. The observable universe contains at least 2 trillion galaxies, each one potentially as large or larger than ours. And the space between them? That's where things get truly incomprehensible. If you're using this to fall asleep, that's literally why I make them. So, subscribe maybe and tell me where you are and what time. I check comments and it's like Tokyo at midnight, Chicago at dawn all at once. You know that feeling when you try to picture something so big that your brain just sort of gives up? That's what we're dealing with here. The difference between our galaxy and the universe isn't like comparing a house to a city. It's like comparing a single atom to the entire planet Earth. Actually, that's not even close. The real comparison is so much more extreme that we don't have good metaphors for it. And here's the really crazy part. We only discovered the universe was bigger than our galaxy 100 years ago. Before 1924, humanity thought the Milky Way was everything, the entire cosmos, all of existence. We were so wrong, it's almost funny. Let's start with what we can barely understand. Our galaxy. The Milky Way is a barred, spiral galaxy containing somewhere between 100 billion and 400 billion stars. Nobody knows the exact number because, well, counting stars is hard when you're inside the thing you're trying to count. Our Sun is just one of those stars, located about 26,000 light-years from the galactic center. We're in a minor spiral arm called the Orion Spur, basically cosmic suburbia. Not in the exciting core, not in the outer reaches, just somewhere in the middle thirds of the disk. The Milky Way's disk is about 100,000 light-years across. To put that in perspective, light from one edge of our galaxy takes 100,000 years to reach the other edge. The fastest spacecraft humans have ever built, Voyager 1, is currently traveling at about 38,000 miles per hour. At that speed, it would take roughly 1.6 billion years to cross the galaxy. Billion. With a B. But that's just the disk. The Milky Way also has a roughly spherical halo of older stars and globular clusters extending maybe 130,000 light-years from the center. And then there's the dark matter halo, which we can't see but know exists because of its gravitational effects. That extends maybe 1 million light-years out. So depending on how you measure it, our galaxy has a diameter somewhere between 100,000 and 1 million light-years. Let's use 100,000 for the visible part, because that's what most people mean when they talk about galactic size. Now, 100,000 light-years is already a number so big it's meaningless to human brains. We didn't evolve to comprehend distances like that. Our ancestors needed to understand distances like that watering hole is 2 days' walk away, or that predator is 50 yards off and closing fast. Galactic distances? Our brains just shrug. But hold on, because we're about to make the Milky Way seem incredibly, impossibly small. The observable universe, the part of the universe we can theoretically see, has a diameter of about 93 billion light-years. Wait, you might be thinking, didn't you say the universe is only 13.8 billion years old? How can light have traveled 93 billion light-years if the universe has only existed for 13.8 billion years? Great question. The answer is cosmic expansion. The universe isn't just sitting still while light travels through it. The universe itself is expanding. Space is stretching. So the most distant objects we can see started out much closer to us. but the space between us and them has been expanding. The whole time light was traveling from them to us. Objects that emitted light 13.8 billion years ago are now roughly 46.5 billion light-years away from us in any direction. That's why the observable universe has a diameter of 93 billion light-years, even though it's only 13.8 billion years old. Still with me? Good, because now comes the part where your sense of scale just evaporates. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years across. Do the division and you get 930,000. The observable universe is nearly 1,000,000 times wider than our galaxy. But that doesn't capture it at all, because we're talking about three-dimensional space. When you compare volumes instead of diameters, the numbers get truly stupid. The volume of a sphere is 4/3 times pi times the radius cubed. The Milky Way's radius is 50,000 light-years. Cube that and you get 125 trillion cubic light-years. That's 125 with 24 zeros after it. The observable universe's radius is 46.5 billion light-years. Cube that. You get a number so large it's hard to even write down properly. About 420 septillion cubic light-years. That's 420 with 24 zeros. So by volume, the observable universe is about 800 trillion times larger than the Milky Way. Not thousand, not million, not billion, trillion. 800 trillion Milky Ways could fit inside the observable universe. And remember, that's just the observable universe. The actual universe is almost certainly much, much larger. Possibly infinite. We'll get to that nightmare in a bit. First, let's talk about how we even figured this out, because the story is one of the most important in human history, and almost nobody knows it. For most of human existence, we thought the stars were just lights stuck to a celestial sphere surrounding Earth. Even after Copernicus and Galileo proved that Earth orbited the Sun, people still thought the stars were relatively close, all roughly the same distance away, all part of a single cosmic structure. Then, in 1610, Galileo pointed his telescope at a fuzzy patch in the night sky that had been called a nebula, Latin for cloud. Through the telescope, he saw it was actually a collection of countless stars, too faint and distant to see individually with the naked eye. The Milky Way wasn't a cloud. It was a river of stars. Over the next 300 years, astronomers gradually mapped the Milky Way and started to understand we were inside a disk-shaped collection of stars. But they still thought this was everything. The entire universe was the Milky Way, except there were these other fuzzy patches scattered around the night sky. Andromeda Nebula, for example, visible to the naked eye under dark skies as a small smudge. Through telescopes, they looked like spiral clouds of gas. Some astronomers thought these nebulae were just gas clouds inside our galaxy, maybe places where new stars were forming. Others suspected they might be separate galaxies far beyond the Milky Way, what they called island universes. But nobody could prove it either way. The debate came to a head in 1920 at what's now called the Great Debate, a formal discussion between astronomers Harlow Shapley and Heber Curtis at the Smithsonian. Shapley argued the Milky Way was the entire universe, and the spiral nebulae were inside it. Curtis argued the spiral nebulae were separate galaxies far outside the Milky Way. They couldn't settle it because they didn't have good distance measurements. They needed a way to figure out how far away the spiral nebulae actually were. Enter Edwin Hubble. Not the telescope, the guy the telescope was named after. In 1923, using the 100-inch telescope at Mount Wilson Observatory in California, then the most powerful telescope in the world, Hubble managed to resolve individual stars in the Andromeda Nebula. More importantly, he identified a type of star called a Cepheid variable. These stars pulse with a regular rhythm, and crucially, there's a direct relationship between how fast they pulse and how intrinsically bright they are. If you measure how fast a Cepheid pulses, you know how bright it actually is. Then you compare that to how bright it looks from Earth, and you can calculate how far away it must be. It's like seeing a candle in the distance and knowing exactly how bright that type of candle is when you're standing right next to it. If it looks dim, it's far away. If it looks bright, it's close. Hubble measured Cepheid variables in Andromeda and did the math. Andromeda was at least 900,000 light-years away. That's 9 times the diameter of the Milky Way as they understood it at the time. Andromeda couldn't possibly be inside our galaxy. It had to be a separate galaxy. In 1924, Hubble published his findings. Overnight, the universe got 1,000,000 times bigger. Humanity realized we weren't just on a planet orbiting a star. We were on a planet orbiting a star inside a galaxy, and that galaxy was just one of countless other galaxies scattered through space. It was like thinking you lived in the only house in the world, then walking outside and seeing millions of other houses stretching to the horizon in every direction. But Hubble wasn't done. He kept measuring distances to more and more galaxies. And in 1929, he noticed something strange. The galaxies were moving. All of them were moving away from us. And the farther away a galaxy was, the faster it was receding. This is cosmic expansion. The universe isn't static. It's growing. Space itself is stretching, carrying galaxies apart like raisins in rising bread dough. This observation led directly to the Big Bang theory. If galaxies are moving apart now, they must have been closer together in the past. Wind the clock back far enough, and everything in the universe must have been compressed into an unimaginably small, dense, hot state. Then, about 13.8 billion years ago, space started expanding. The Big Bang wasn't an explosion in space. It was an expansion of space itself. And it's still happening. Right now, as you read this, the universe is getting bigger. Space is stretching. Distant galaxies are moving away from us faster and faster. But here's where things get weird. The universe isn't just expanding. It's expanding faster than light. Wait, you say? I thought nothing could go faster than light. That's right. Nothing can move through space faster than light. But space itself can expand faster than light. There's no speed limit on the expansion of space itself. This means there are galaxies so far away that the space between us and them is expanding faster than light could ever cross that distance. Light from those galaxies will never reach us. Not in 1,000,000,000,000 years. Not in a Google years. Never. These galaxies are beyond our cosmic horizon. They exist, but they're fundamentally unreachable and unobservable. As far as we're concerned, they might as well be in a different universe. And every second, more galaxies cross this horizon. Galaxies that we can see today will eventually recede beyond the cosmic horizon and disappear from view forever. The observable universe is shrinking in terms of what we'll eventually be able to see, even as the universe itself gets bigger. Right now, we can observe about 2 trillion galaxies. That's the current estimate based on deep field observations from telescopes like Hubble. But many of those galaxies are already beyond the point where we could ever reach them, even if we traveled at the speed of light forever. We're seeing ancient light that left those galaxies billions of years ago. The galaxies themselves have since moved so far away that space between us and them is expanding faster than we could ever cross it. Let me give you a sense of the scale here. Our nearest large galactic neighbor is Andromeda, about 2.5 million light-years away. That's relatively close in cosmic terms. In fact, Andromeda is one of the few galaxies moving toward us rather than away. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge into a single, larger galaxy. Don't worry. Stars are so far apart that, even during a galactic collision, individual stars almost never actually hit each other. Picture that collision for a moment. Two massive spiral galaxies, each containing hundreds of billions of stars, slowly drifting together over millions of years. As they approach, their gravitational fields start interacting. Stars get pulled into new orbits. Gas clouds collide and trigger massive bursts of star formation. The supermassive black holes at each galaxy's center spiral toward each other, eventually merging into an even larger black hole. The whole process takes about 1 billion years from the first contact to final merger. During that time, the night sky from Earth, if Earth still exists, would be spectacular. Andromeda would grow larger and larger, transforming from a faint smudge to a brilliant river of stars stretching across half the sky. New stars would be forming at a furious rate, visible as bright blue regions where gas clouds are colliding. The merged galaxy, which astronomers have already nicknamed Milkomeda, would be an elliptical blob rather than a spiral, all the elegant structure of both galaxies scrambled by their violent union. But move beyond our local group of galaxies and things get distant fast. The Virgo supercluster, a collection of galaxy groups including our local group, is about 65 million light-years across. That's 650 times the diameter of the Milky Way. Beyond that, there's the Laniakea supercluster, defined in 2014, which is about 520 million light-years in diameter. Our galaxy is a tiny dot in one small corner of Laniakea, which itself is just one of millions of superclusters in the observable universe. The discovery of Laniakea was remarkable in its own right. Astronomers mapped the motions of thousands of galaxies, tracking which direction they were moving. They found that galaxies weren't just moving away from each other due to cosmic expansion. They were also moving relative to each other due to gravity. Large concentrations of mass were pulling nearby galaxies toward them. When they mapped these motions, a pattern emerged. All the galaxies in a vast region of space, including the Milky Way, were being pulled toward a central region astronomers called the Great Attractor. This motion defined the boundaries of Laniakea, our cosmic home at the supercluster scale. Laniakea contains about 100,000 galaxies, with a total mass of about 100 quadrillion times the mass of the Sun. That's roughly 1,000 times the mass of the Milky Way. It's a structure so vast that light takes 520 million years to cross it. And it's just one supercluster among millions. Here's what breaks your brain. All of this, everything I just described, all the galaxies and superclusters and cosmic filaments, all 2 trillion galaxies scattered across 93 billion light-years, all of it together makes up less than 5% of the universe. The rest is dark matter and dark energy. About 27% dark matter, about 68% dark energy. We don't know what either of them actually is. We just know they exist because of their effects. Dark matter doesn't emit light or any other electromagnetic radiation, but it has mass and creates gravitational effects. We know it's there because galaxies rotate too fast. Based on the visible matter in a galaxy, stars on the outer edges should fly off into space. But they don't. because there's invisible mass holding them in place. Dark matter. The discovery of dark matter came from astronomer Vera Rubin in the 1970s. She was measuring rotation curves of spiral galaxies, tracking how fast stars orbit at different distances from the galactic center. According to Newton's laws and what we could see, stars far from the center should orbit much slower than stars near the center, just like outer planets in our solar system orbit slower than inner planets. But that's not what she found. Stars at the edge of galaxies were orbiting just as fast as stars near the center. This made no sense unless there was a lot of invisible mass spread throughout the galaxy. Mass we couldn't see, but that was gravitationally affecting everything. This discovery was revolutionary and initially controversial. But over time, more and more evidence accumulated. Galaxy clusters showed the same problem. Gravitational lensing, where light from distant objects is bent by the gravity of closer objects, revealed that clusters contained far more mass than their visible matter could account for. Computer simulations of cosmic structure formation couldn't reproduce what we actually see unless they included dark matter. Now, we know that every galaxy is surrounded by a massive halo of dark matter. The Milky Way's dark matter halo might extend 1 million light-years from the galactic center, 10 times farther than the visible disk. Most of the mass of our galaxy is invisible. What is dark matter? We don't know. The leading theory is that it's made of particles that don't interact with electromagnetic radiation, so they don't emit, absorb, or reflect light. They only interact through gravity and possibly through the weak nuclear force. Physicists call these hypothetical particles WIMPs, weakly interacting massive particles. Despite decades of searching, we haven't detected dark matter particles directly. We see their gravitational effects everywhere we look, but the particles themselves remain elusive. It's like knowing there's an invisible elephant in the room because you can see its footprints and feel it bumping into things, but you can't see or touch the elephant itself. Experiments deep underground in old mines are looking for dark matter particles. The idea is that dark matter is constantly passing through Earth, passing through everything, occasionally colliding with ordinary matter. These collisions would be incredibly rare, which is why we need giant detectors shielded from all other particles by tons of rock. So far, nothing. No confirmed detections, just upper limits on how often dark matter collides with normal matter, getting tighter year by year. Maybe dark matter doesn't interact with normal matter at all, except through gravity. Maybe it's something even stranger than particles, some aspect of space and time we don't understand. Maybe our theories of gravity are wrong, and we don't need dark matter at all. But that last option seems unlikely, given how well dark matter explains so many different observations. Dark energy is even stranger. It's a property of space itself that causes cosmic expansion to accelerate. The universe isn't just expanding. It's expanding faster and faster over time. Something is pushing the universe apart, and we call that something dark energy. We have no idea what it actually is. The discovery of dark energy was even more shocking than dark matter. In the 1990s, 2 teams of astronomers were using Type Ia supernovae to measure cosmic expansion at different distances. They expected to find that expansion was slowing down due to gravity pulling everything back together. Instead, they found the opposite. Expansion was accelerating. This made no sense according to any theory anyone had. Gravity is attractive. It should slow expansion. but something was counteracting gravity, something that became stronger as the universe got larger. The farther apart galaxies got, the faster they moved apart. The simplest explanation is that empty space itself has energy. This vacuum energy, also called the cosmological constant, creates a kind of repulsive force that pushes space apart. The more space there is, the more vacuum energy there is, so the force keeps getting stronger. But here's the problem. When physicists calculate how much vacuum energy should exist based on quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. Their theoretical prediction is 1 followed by 120 zeros times larger than what we actually observe. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. Either our theories are catastrophically wrong, or there's some mechanism we don't understand that almost perfectly cancels out the vacuum energy, leaving just a tiny residual amount that we observe as dark energy. Whatever dark energy is, it makes up 68% of the universe. It's the dominant component of reality, and we have no idea what it is or why it exists. So when we compare the size of our galaxy to the universe, we're really only comparing visible matter. The full picture includes vast amounts of invisible stuff that we barely understand. The universe is made mostly of things we can't see and don't understand, operating according to principles we're still trying to figure out. But even just the visible universe, the part we can see and measure, is so large that it defeats comprehension. Think about it this way. You're on Earth. Earth is 8,000 miles wide. Earth orbits the Sun at a distance of 93 million miles. That distance, Earth to Sun, is called an astronomical unit. The solar system, if you count the Oort cloud, extends about 100,000 astronomical units from the Sun. That's about 1.6 light years. The Oort cloud is a spherical shell of icy bodies surrounding the solar system, remnants from when the planets formed. It's so far out that the Sun appears as just a bright star. Objects in the Oort cloud take millions of years to complete a single orbit. The Milky Way is 100,000 light years across. That's 62,500 times wider than the solar system. The observable universe is 93 billion light years across. That's 930,000 times wider than the Milky Way, which is 62,500 times wider than the solar system, which is about 1,000,000 times wider than Earth. Multiply it out, and the observable universe is about 580 trillion times wider than Earth. If Earth were a grain of sand 1 millimeter across, the observable universe would be about 580 billion kilometers wide. That's roughly 4,000 times the distance from Earth to the Sun. And that's just comparing diameters. Compare volumes and the numbers become genuinely meaningless. The observable universe contains a volume of space so vast that if you tried to count every cubic meter of it, 1 per second, it would take trillions of years. Far longer than the current age of the universe. Now, let's pause and really think about what the Milky Way actually is, because understanding our galaxy helps us appreciate just how absurd it is that the universe contains trillions of them. The Milky Way isn't just a collection of stars floating in space. It's a complex, dynamic system with structure and history. At the center is a supermassive black hole called Sagittarius A star, with a mass of about 4 million times that of our Sun. This black hole is relatively quiet right now, not actively feeding on matter and producing intense radiation. But it occasionally flares up when a gas cloud or unfortunate star wanders too close and gets torn apart by tidal forces. Around this black hole, the central bulge contains some of the oldest stars in the galaxy, many of them 10 billion years old or more. These old stars are red giants and red dwarfs, stars that have been burning for so long they've exhausted most of their hydrogen fuel. They're the stellar equivalent of retirees, no longer young and energetic, just slowly fading away over billions of years. The disk, where we live, is where most of the star formation happens. It's divided into spiral arms, regions of higher density, where gas clouds collapse to form new stars. The spiral arms aren't fixed structures like the blades of a pinwheel. They're density waves that move through the disk like ripples on a pond. Stars and gas clouds pass through these arms, get compressed by the higher density, and sometimes trigger bursts of star formation. Our Sun is located in the Orion Spur, a minor arm between two major spiral arms called Perseus and Sagittarius. We're about 26,000 light-years from the center, roughly halfway out to the edge of the disk. It's a quiet neighborhood, cosmically speaking. No major star-forming regions nearby. No recent supernova. Just an average star in an average location, which is probably good for the development of life. Too close to the galactic center and the intense radiation from the supermassive black hole and dense star clusters would sterilize any planets. Too far out, and there wouldn't be enough heavy elements to form rocky planets in the first place. Our Sun orbits the galactic center at about 514,000 miles per hour. That sounds incredibly fast, and it is by human standards, but at galactic scales it's leisurely. Even at that speed, it takes about 225 million years to complete one orbit. The last time we were at this position in the galaxy, dinosaurs hadn't evolved yet. Reptiles were just starting to dominate the land. The supercontinent Pangaea wouldn't form for another 75 million years. By the time we complete another orbit, 225 million years from now, who knows what Earth will look like? Humans will almost certainly be gone, either extinct or evolved into something we wouldn't recognize. The continents will have drifted into new configurations. Africa is slowly splitting apart along the East African Rift. In a few tens of millions of years, it might be two separate continents. The Atlantic Ocean is getting wider, pushing the Americas away from Europe and Africa. The Pacific is shrinking. Eventually, hundreds of millions of years from now, the continents might merge again into a new supercontinent. New mountain ranges will have risen where tectonic plates collide. The Himalayas will be eroded away. The climate will have changed countless times, cycling between ice ages and warm periods. Entire ecosystems will have appeared and vanished. New species will have evolved to fill ecological niches we can't even imagine. But the Milky Way will still be here, still slowly rotating, still forming new stars in its spiral arms, still eating smaller galaxies. The Milky Way is also eating other galaxies. Right now, it's in the process of absorbing several smaller dwarf galaxies. The Sagittarius dwarf galaxy is being ripped apart by the Milky Way's gravity, its stars slowly joining our galaxy's halo. You can see streams of stars from this galaxy stretched out across the sky, like taffy being pulled apart. The Canis Major dwarf galaxy is meeting a similar fate, leaving its own trail of stars as it's consumed. This process is called galactic cannibalism, and it's how large galaxies grow. The Milky Way has consumed dozens of smaller galaxies over its lifetime, absorbing their stars and gas and adding them to its own mass. Astronomers can even identify streams of stars in the galactic halo that originated in these consumed galaxies, like fossils showing the Milky Way's dietary history. Each stream has a slightly different chemical composition, revealing which dwarf galaxy it came from and when the merger happened. Some of these mergers occurred billions of years ago. Others are happening right now. The Milky Way is still actively growing through cannibalism, and it will continue to do so for billions of years. This is normal. Galaxies don't exist in isolation. They interact, merge, collide. Our eventual collision with Andromeda isn't unusual. It's just galactic evolution, the way the universe operates at the largest scales. In the early universe, small galaxies formed first. Over time, they merged into larger galaxies. Those larger galaxies merged into even larger ones. This hierarchical growth continues today. The largest galaxies in the universe, massive ellipticals like IC 1101, formed from countless mergers over billions of years. But even with all this complexity, all this structure, all these hundreds of billions of stars, the Milky Way is just one galaxy. Average-sized, actually. Some galaxies are much smaller, containing only a few billion stars. Dwarf galaxies like the small Magellanic Cloud have maybe 3 billion stars. Ultra-faint dwarf galaxies might have only a few thousand stars, barely qualifying as galaxies at all. They're more like giant star clusters. On the other end of the scale, giant elliptical galaxies can contain over 100 trillion stars. IC 1101, one of the largest galaxies we've discovered, contains more than 100 trillion stars. That's more than 200 times the number of stars in the Milky Way. IC 1101 is about 6 million light-years across, roughly 60 times the diameter of the Milky Way. It's an elliptical galaxy, a diffuse blob of old stars with no spiral structure, no ongoing star formation, no elegant arms or dust lanes, just a vast swarm of ancient red and yellow stars orbiting a central supermassive black hole that probably has a mass of several billion suns. It formed from the merger of many smaller galaxies over billions of years, accumulating mass until it became one of the most massive galaxies in the observable universe. It's so large that the Milky Way and Andromeda combined would still be dwarfed by it. You could fit 60 Milky Ways across IC 1101's diameter. By volume, you could fit hundreds of thousands of Milky Ways inside IC 1101. But even IC 1101, a monster galaxy that dwarfs the Milky Way, is still just a tiny speck in the cosmic web. Because galaxies aren't distributed randomly through space. They're organized into structures so large that galaxies become the individual units, the way atoms are the building blocks of matter. At the largest scales, galaxies are just the pixels that make up the picture of cosmic structure. Start with galaxy groups. The Milky Way is part of the local group, a collection of about 80 galaxies dominated by 3 large spirals: the Milky Way, Andromeda, and Triangulum. The rest are smaller dwarf galaxies, most of them satellites of the big 3. The local group is about 10 million light-years across. That's 100 times the diameter of the Milky Way. The local group is gravitationally bound. Despite cosmic expansion, these galaxies aren't moving apart. They're held together by their mutual gravity, orbiting each other like a giant cosmic dance that plays out over billions of years. Over time, many of the smaller galaxies will be consumed by the larger ones. Eventually, billions of years from now, the local group will probably merge into a single massive elliptical galaxy containing all the stars that currently belong to its member galaxies. Galaxy groups cluster into galaxy clusters. The nearest large cluster to us is the Virgo cluster, containing over 1,500 galaxies spread across about 15 million light-years. It's dominated by several massive elliptical galaxies, including M87, which contains one of the largest supermassive black holes we know about. with a mass of about 6.5 billion times that of the Sun. This is the black hole that was photographed by the Event Horizon Telescope in 2019, the first direct image of a black hole ever captured. That image was remarkable. It showed a bright ring of light surrounding a dark circle, the shadow of the black hole's event horizon. The light comes from superheated matter swirling around the black hole at nearly the speed of light, reaching temperatures of billions of degrees. The dark circle in the middle is the event horizon, the point of no return beyond which nothing, not even light, can escape. The Virgo cluster is located about 65 million light-years from Earth. It's so massive that its gravity is actually pulling the local group toward it. We're falling into the Virgo cluster at about 400 kilometers per second, though we won't arrive for billions of years. By the time we get there, the Milky Way and Andromeda will have already merged, and who knows what the universe will look like. Galaxy clusters, in turn, are part of superclusters. The Virgo cluster and our local group are both part of the Laniakea supercluster, a structure containing about 100,000 galaxies spread across 520 million light-years. That's 5,200 times the diameter of the Milky Way. Laniakea isn't gravitationally bound the way galaxy groups and clusters are. It's too large for gravity to overcome cosmic expansion at these scales. Instead, it's more of a flow pattern, a region of space where galaxies are all being pulled in the same general direction by a massive concentration of matter. The name Laniakea means immense heaven in Hawaiian, which seems appropriate given the scale. It's a heaven we'll never see the full extent of, a structure so vast that light takes 500 million years to cross it. And superclusters are organized into even larger structures called galaxy filaments. These are the largest structures in the universe, vast walls and sheets of galaxies separated by enormous voids. The Sloan Great Wall, one of the largest known structures in the universe, is a galaxy filament about 1.4 billion light-years long. That's 14,000 times the diameter of the Milky Way. It contains hundreds of thousands of galaxies arranged in a long, thin sheet, like a cosmic wall separating two vast empties. Even larger is the Hercules Corona Borealis Great Wall, possibly the largest structure in the observable universe, at about 10 billion light-years across. That's more than 10% of the diameter of the observable universe. It contains billions of galaxies arranged in an unimaginably vast superstructure. To put this in perspective, light traveling at 186,000 miles per second takes 10 billion years to cross the Hercules Corona Borealis Great Wall. The entire age of Earth is only 4.5 billion years. You could fit two Earths, from formation to present day, into the time it takes light to cross this single structure. The dinosaurs appeared and went extinct while light was crossing from one side to the other. These filaments surround voids, regions of space that contain very few galaxies. The voids are huge, often hundreds of millions of light-years across. The Botas void, one of the largest known, is about 330 million light-years in diameter and contains only about 60 galaxies, in a volume where you'd expect to find thousands based on the average density of the universe. Imagine floating in the middle of the Botas void. You'd look out in all directions and see almost nothing. A handful of distant galaxies, faint smudges barely visible, but mostly just darkness. Empty space, stretching for hundreds of millions of light-years in every direction. It would be one of the loneliest places in the universe. The first time astronomers mapped these voids in the 1980s, it was shocking. They had expected galaxies to be distributed more or less randomly through space, maybe with some clumping due to gravity, but no large-scale structure. Instead, they found that the universe looks like a sponge, or a network of bubbles at the largest scales, with galaxies concentrated in thin filaments and walls surrounding vast empty regions. This is the cosmic web, the large-scale structure of the universe. From far enough away, if you could somehow step back and see the full observable universe at once, it would look like a three-dimensional spider web made of galaxies, with huge empty spaces between the threads. This structure formed from tiny variations in density in the early universe. Right after the Big Bang, matter was distributed almost perfectly uniformly. Almost, but not quite. There were tiny fluctuations, regions that were slightly more dense or slightly less dense than average. These variations were incredibly small, less than 1 part in 100,000. If the early universe had been perfectly smooth, we wouldn't be here. No stars, no galaxies, no planets, no life. Just a thin, uniform gas expanding forever. But those tiny imperfections saved us. Over time, gravity amplified these differences. Regions that were slightly more dense attracted more matter. As they grew denser, their gravity got stronger, so they attracted even more matter. Meanwhile, regions that were slightly less dense lost matter to their denser neighbors, becoming voids. Over billions of years, these density differences grew exponentially, pulling matter into filaments and leaving voids behind. The process is like what happens when you drain a bathtub. The water doesn't flow out uniformly. It forms whirlpools and currents and flows, organized patterns emerging from tiny initial differences in velocity and position. The cosmic web is visible in surveys like the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies. When you plot all those galaxies in 3 dimensions, the filamentary structure becomes clear. It's one of the most beautiful patterns in nature, visible only at the largest possible scales. You have to zoom out so far that galaxies become individual pixels before you can see the pattern. Computer simulations can reproduce this structure remarkably well. If you start with the conditions of the early universe, as revealed by observations of the cosmic microwave background, and then simulate the gravitational evolution of matter over billions of years, you get a cosmic web that looks just like what we observe. The simulations match reality down to surprisingly fine details. This is one of the strongest pieces of evidence that we understand how the universe evolved, even if we don't understand what most of it is made of. We can model the growth of structure from the Big Bang to today with remarkable accuracy. We just have to include dark matter and dark energy in the models, these mysterious components we can't see or understand, but that clearly dominate the universe. And all of this structure, all these filaments and voids and superclusters, all of it fits within the observable universe, the 93 billion light-year sphere that represents how far light has been able to travel since the Big Bang, adjusted for cosmic expansion. But here's the thing that really melts your brain. The observable universe isn't a special place. It's not the center of anything. It's not an unusual region. It's just the region we can see from our particular location in space and time. If you traveled to a galaxy 10 billion light-years away, you'd have a different observable universe centered on that galaxy. You'd see galaxies that are invisible to us because they're beyond our horizon, and some galaxies visible to us would be beyond your horizon. Every point in space has its own observable universe, its own cosmic horizon, its own sphere of visibility, determined by how far light has been able to travel from that point. and these observable universes overlap. The galaxy you can see at the edge of your horizon can see other galaxies beyond your horizon. Those galaxies can see still other galaxies even farther out. It's like a network of overlapping circles, each one representing what's visible from a particular location. This is like being at sea, where the horizon is about 3 miles away in every direction. You can see ships up to 3 miles away. Those ships can see other ships, another 3 miles beyond them. Ships that are invisible to you because they're beyond your horizon. The total area containing ships might extend dozens or hundreds of miles, but you can only see a small circle around yourself, determined by how far light can travel before the curvature of Earth blocks your view. The universe works the same way, except the horizon is 46.5 billion light-years instead of 3 miles, and it's determined by cosmic expansion rather than planetary curvature. Objects beyond that distance are receding faster than light, so their light will never reach us. They exist, but they're causally disconnected from us. Nothing they do can ever affect us, and nothing we do can ever affect them. So what's beyond our cosmic horizon? More galaxies, more structure, more of the same basic stuff, as far as we can tell. The universe appears to be roughly homogeneous at large scales, meaning it looks basically the same in all directions when you average over large enough volumes. This is called the cosmological principle, and it's one of the fundamental assumptions of modern cosmology. If the cosmological principle is correct, and all evidence suggests it is, then the universe beyond our horizon looks similar to what we see within our horizon. More galaxy filaments, more voids, more superclusters. Just more of everything. The cosmic web extends beyond what we can see, probably forever, or at least for distances vastly larger than the observable universe. But how much more? That's where things get speculative and slightly terrifying. The minimum size for the universe, if it's finite, is probably at least 250 times larger than the observable universe. This comes from measurements of the universe's curvature using the cosmic microwave background. Space can be flat, positively curved like the surface of a sphere, or negatively curved like a saddle. If space is curved, we should be able to detect that curvature by looking at patterns in the cosmic microwave background. Specifically, we'd see patterns at certain angular scales that would tell us whether space curves back on itself. So far, we've detected no curvature. Space appears flat within our measurement precision, which is very high. The measurements from satellites like WMAP and Planck can detect curvature if the radius of curvature is less than about 250 times the radius of the observable universe. Either space is exactly flat, which would make the universe infinite, or it has some tiny amount of curvature that's too small for us to measure. If there's any curvature at all, the universe must curve back on itself at distances much larger than the observable universe. The minimum radius of curvature that's consistent with our measurements is about 250 times the radius of the observable universe. 250 times larger in diameter means about 15 million times larger in volume, because volume scales as the cube of diameter. So instead of 2 trillion galaxies in the observable universe, the full universe would contain at least 30 quadrillion galaxies. That's 30,000 trillion. Each one a complex system containing billions or hundreds of billions of stars. Each star potentially surrounded by planets. Each planet potentially a home for life. And that's the minimum. The universe could be vastly larger than that. Inflation theory, which explains why the universe is so uniform and flat, predicts that the universe should be enormously larger than the observable portion. Some inflationary models suggest the universe could be googles of times larger than the observable universe. A google is 1 followed by 100 zeros. That's a number larger than the number of atoms in the observable universe. A universe that size would contain more galaxies than there are atoms in everything we can see. More stars than there are quantum states in all the matter within our cosmic horizon. At scales like that, numbers stop having meaning. Our brains can't process a google of anything. It's effectively infinite for any practical purpose. Other models suggest the universe might actually be infinite. Just flat space extending forever in all directions, filled with galaxies and structure with no edge, no boundary, no end. In an infinite universe, everything that's possible happens somewhere. Everything that could exist does exist infinitely many times, scattered across infinite space. There would be infinitely many galaxies like the Milky Way, infinitely many solar systems like ours, infinitely many planets exactly like Earth, infinitely many people exactly like you, living lives exactly like yours, reading this exact sentence at this exact moment. There would also be infinitely many versions of you living slightly different lives. Versions where you made different choices, where different things happened, where your life went in a different direction. Every possible variation of your life would exist somewhere in an infinite universe, infinitely many times. It's a strange and unsettling idea, but it's consistent with observations. We can't rule it out. An infinite universe is one of the possibilities we have to take seriously. Both possibilities, finite but enormous or actually infinite, are compatible with what we observe. We genuinely don't know which one is true, and we might never know because the regions that could tell us are beyond our cosmic horizon, forever out of reach. The universe might be hiding its true nature from us, not out of any malice or design, but simply because cosmic expansion has placed the relevant information beyond where light can ever reach us from. But even the observable universe, the part we can see and measure and study with telescopes, contains numbers that completely break human intuition. 2 trillion galaxies, at minimum, each containing an average of maybe 100 billion to 200 billion stars. That's somewhere between 200 and 400 sextillion stars in the observable universe. Every single one of those stars is a sun, a massive nuclear furnace, fusing hydrogen into helium and releasing energy, potentially warming planets that might orbit it. And many of those stars have planets. Probably most of them. The Kepler Space Telescope, during its mission from 2009 to 2018, revolutionized our understanding of planetary systems. It discovered over 2,600 confirmed exoplanets by staring at just one tiny patch of sky containing about 150,000 stars. It detected planets by watching for tiny dips in starlight when a planet passed in front of its star. Based on its observations, astronomers estimate that on average, every star in our galaxy has at least one planet. Some stars have many planets, like our Sun with its 8. Some have none, but the average is at least one planet per star, probably more. Extrapolate that to the entire Milky Way, and there are probably 200 billion to 400 billion planets in our galaxy alone. Rocky planets like Earth, as opposed to gas giants like Jupiter, might number 50 billion or more. Planets in the habitable zone, the region where liquid water could exist on the surface, might number 10 billion to 40 billion in the Milky Way. Now, multiply those numbers by 2 trillion galaxies. You get numbers so large they stop having any meaningful connection to human experience. at least 200 sextillion planets in the observable universe. Probably more, maybe much more. Tens of sextillions of those planets are probably rocky worlds similar to Earth in size and composition. Sextillions of them are probably in their star's habitable zone, the Goldilocks region where it's not too hot and not too cold for liquid water. The sheer number of potential homes for life is staggering beyond any comprehension. If you tried to count all the potentially habitable planets in the observable universe, counting one per second, it would take you trillions of years, longer than the current age of the universe. How many of those planets might harbor life? We don't know. Earth is our only example, our only data point. Life here emerged relatively quickly after the planet formed, within the first billion years. The Earth formed about 4.5 billion years ago. The oldest evidence for life dates to about 3.7 billion years ago, maybe earlier. That suggests life might be common wherever conditions are right, that the jump from chemistry to biology might be relatively easy given the right ingredients and environment. But we've found no evidence of life anywhere else in the universe. No radio signals from alien civilizations. No artifacts in our solar system. No obvious signs of astroengineering when we look at distant stars. No patterns in the light from exoplanets that would indicate an oxygen-rich atmosphere produced by photosynthesis. We're looking. We're listening. But so far, silence. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" If the universe is so vast, if there are so many stars and planets, if life is even moderately common, then where are all the alien civilizations? Why haven't we detected any sign of them? There are lots of possible answers, and none of them are particularly comforting. Maybe life is actually rare despite the enormous number of possible homes. Maybe the jump from non-life to life requires conditions so specific, so unlikely, that even with sextillions of planets, only a handful have ever produced living organisms. Maybe Earth is a cosmic fluke, a one in a sextillion accident. Or maybe life is common, but intelligence is rare. Earth had life for over 3 billion years before any species developed technology. For most of Earth's history, the most complex life forms were single-celled bacteria. Multicellular life didn't appear until about 600 million years ago. Complex animals with brains and nervous systems are less than 500 million years old. Intelligent, tool-using species like humans have only existed for a few million years at most. Technological civilization capable of sending signals into space has only existed for about 100 years, and we've only been sending strong signals for about 80 years. Maybe that's normal. Maybe most planets with life never develop intelligence. Maybe the evolutionary path from bacteria to radio telescopes is so unlikely, requires so many specific accidents and contingencies, that it almost never happens. Maybe Earth is unusual in having produced a species capable of asking questions about the universe. Or maybe technological civilizations are common, but they don't last long. Maybe the same technologies that allow civilizations to send signals into space also give them the power to destroy themselves. Nuclear weapons, climate change, artificial intelligence, nanotechnology, biological warfare. Maybe most civilizations last only a few hundred years after developing technology before they self-destruct. If that's the case, then at any given moment, there might be millions or billions of technological civilizations scattered across the observable universe, but they're so short-lived and so far apart that they never overlap in time and space. each one arises, flourishes briefly like a match flaring in the darkness, and vanishes before any others become aware of their existence. Or maybe space is just too vast. Even if there are millions of technological civilizations in the universe right now, sending out radio signals and trying to make contact, they might be separated by such enormous distances that communication is impossible. The nearest one might be in another galaxy, tens of millions of light years away. Even if they're sending signals in all directions, those signals would take tens of millions of years to reach us. By the time we received them, that civilization would be long gone, extinct or evolved beyond recognition. And even if we did detect a signal from another galaxy, what would we do? We couldn't respond. By the time our response arrived, hundreds of millions of years would have passed. Entire species would have evolved and gone extinct. Continents would have moved. Stars would have been born and died. The civilization that sent the original signal would be dust. The universe might be full of civilizations, all of them shouting into the void, none of them ever hearing a response because the distances are simply too great and the timescales too long for meaningful communication. That's perhaps the loneliest implication of cosmic scale. Not that we might be alone, but that we might not be. And it doesn't matter because the universe is so vast that we'll never reach each other, never communicate, never even know the other exists. Each civilization trapped in its own cosmic island, its own cluster of reachable galaxies, forever separated from all the other islands by expanding space that nothing can cross. Each one looking up at the night sky and seeing billions of galaxies and wondering if anyone else is out there, never knowing that countless others are asking the same question from their own unreachable islands. But let's come back to what we know for certain, what we can measure, and what we can observe with telescopes and scientific instruments. What's not speculation but established fact. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years across. One is 930,000 times larger than the other by diameter. By volume, the observable universe is 800 trillion times larger than the Milky Way. 800 trillion. That's the number that keeps coming up. 800 trillion Milky Way-sized volumes of space fit inside the observable universe. Each one could potentially contain a galaxy. Many of them do contain galaxies. Some contain massive galaxy clusters. Others are part of the vast voids between filaments, empty, except for the occasional lonely galaxy drifting through the darkness. But even this incomprehensible number probably vastly underestimates the full scale of reality. The observable universe is likely just a tiny fraction of the whole. The actual universe could be thousands or millions or googles of times larger. Or it could be infinite, just extending forever with no edge, no boundary, no center, no special place. Either way, our galaxy is nothing. We're a speck in an ocean so vast that calling it an ocean is insulting to oceans. We're less than a grain of sand on a beach that stretches across the entire surface of Earth and then keeps going into dimensions we can't visualize. And yet, we measured it. We figured it out. We're the tiny speck that refused to accept ignorance, that insisted on understanding no matter how vast and incomprehensible the reality we discovered turned out to be. Humans have existed as a species for maybe 300,000 years. We've had scientific instruments for maybe 500 years. We've had the ability to measure cosmic distances for maybe 100 years. In that incredibly brief span of time, shorter than a single heartbeat on cosmic timescales, we went from thinking the Milky Way was the entire universe to measuring a cosmos so vast that our galaxy is essentially nothing. That's the story of cosmic discovery. That's what we've accomplished. In just a century, we revolutionized our understanding of where we are and what exists. We discovered that the universe is almost unimaginably larger than anyone had dreamed. And it's one of the most remarkable achievements in the history of any species, anywhere, ever. We should be proud of it. We should teach it to our children. We should remember that we're the species that looked up at the night sky and refused to be satisfied with just wondering. We had to know, and we figured it out. The Milky Way is our home, a beautiful spiral galaxy containing hundreds of billions of stars, massive beyond human comprehension, ancient beyond human timescales, complex beyond human understanding. It's the cosmic structure that gave rise to our solar system, our planet, our species. It's where we've spent our entire existence. It's all we've ever known directly. The universe is our context. It's the full reality in which our galaxy exists. It's 800 trillion times larger by volume. It contains 2 trillion other galaxies, each one potentially as complex and ancient and beautiful as our own. It extends across distances so vast that light takes billions of years to cross them. It might be finite but enormous, or it might be infinite. Either way, it's so much larger than our galaxy that the comparison becomes almost meaningless. Understanding the difference between those two scales, grasping even a tiny fraction of the full absurd magnitude of reality, is one of the most profound things a human mind can do. It's humbling. It's terrifying. It's awe-inspiring. It's all of those things at once. You're sitting on a planet orbiting a star in a galaxy that's one of trillions scattered across distances so vast that light takes billions of years to cross them. You're part of a universe so large that your entire galaxy is essentially nothing. A rounding error in the cosmic census, a speck too small to matter in the grand scheme of things. And yet, here you are, conscious, aware, able to think about these questions, able to comprehend, at least partially, the full scale of everything. You're the universe's way of knowing itself. You're the cosmos made conscious. You're the tool reality uses to understand its own existence. That's not nothing. That's everything. The universe might be vast and we might be tiny, but we're the tiny part that can measure the vast part. We're the speck that figured out the ocean. We're the consciousness that comprehended the incomprehensible. And that makes us significant. Not because of our size, not because of our location, not because the universe cares about us in any meaningful way, but because we care. Because we looked up and wondered and investigated and measured and calculated and finally understood, at least a little bit, where we are and what exists. The Milky Way is 100,000 light years across. The universe is 93 billion light years across. One is nearly 1 million times wider than the other, 800 trillion times larger by volume. Those are the numbers. Those are the facts. And they're almost impossible to comprehend, but they're real. And somehow, against all odds, on one tiny planet in one unremarkable corner of one average galaxy, a species evolved that was capable of measuring all of it. That's us. We're the species that figured it out. We're the consciousness that emerged from the cosmos and looked back at itself and really saw, the full, magnificent, terrifying scale of everything. That's what we are. That's what makes us extraordinary. Not our size, but our awareness. Not our cosmic importance, but our determination to understand despite our insignificance. Not what the universe gave us, but what we discovered on our own. You're tiny, you're fragile. You exist for a cosmic instant, but you're also part of the species that measured infinity, or something close enough to it that the difference doesn't matter. And that's absolutely magnificent.